So we've talked about arithmetic. We've talked a little bit about the cubic and the quadratic and the other types of polynomial functions. Today we're talking, the sequences, excuse me. Today we're talking about the geometric sequence, and it is exponential. So the x moves from the base to the exponent, the unknown, okay? So we will be studying these numbers that will have exponential growth or they will have exponential decay, but they will be exponential. Today we're going to focus on just the first side of our note page. So we're just going to do sequences and means. So we have a short period. So today, instructional objective, you'll be able to differentiate between a geometric sequence and a means. We'll pick up the series tomorrow. P.S. Here is a little teaser. Tomorrow I'm going to teach you to add an infinite geometric series and get an answer. I'm going to teach you how to do it. It's possible to add an infinite set of numbers and get an answer. Teach you tomorrow. Okay, also you can apply formulas to evaluate them. So these are the things we're going to do today, focusing on sequences and means. So we're going to start with the definition of geometric sequences, and then after the definition, we'll put it into practice so the definition is just more than words. So a geometric sequence is a sequence in which each term, except for the first term, is found by multiplying the preceding term by the same constant. And I said multiplying. This is what makes it geometric versus arithmetic. Arithmetic, we were adding. Geometric, we're multiplying. Okay? So we will be finding the common ratio instead of the common difference. And we have a formula here that says a sub n is equal to a times r raised to the n minus 1. Now this formula allows us to find any term we want in that sequence. As long as it's not so large, we can't calculate it. Because geometric sequences get large, exceedingly large, or exceedingly small pretty quickly. So you will see answers on today's assignment that are in the 100,000s, or they are tiny, tiny fractions, okay? Because it's exponential, so it grows fast, or it gets tiny fast. So let's define our variables. If we're using this formula, typically what we're looking for is we're looking for the nth term, whatever that is. So this is our nth term. And our a is our first term. R is our common ratio. And I am going to give you a little advice right now on how to find it. I typically will just do a couple of little tests to see if I can get a constant repeat. And I do that by taking this, I'm going to write it as a ratio because it's a ratio. And I'll do it by dividing the second term by the first term. Then I'll check it to make sure I can get a repeat, and I'll do the third term divided by the second term, and I'll do it one more time. And I'll just make sure that the pattern doesn't change by dividing two successive numbers with the larger one on the top or the furthest from position-wise. I'll do the larger position over the smaller position. And that's how you'll find your common ratio. And n is, of course, the number of terms that you're measuring in the sequence. Excuse me. Okay, so here we go. So we have a problem that's 3 parts. So we're going to break it up into part A, B, and C. Excuse me. One more time. Okay, so the first thing we're going to do, the first task, is we're going to write the first 6 terms. So this is going to be part A. And then we'll write the 15th term. That'll be part B. That's 2 different tasks. Of a geometric sequence with our A sub 1 is 3. So there's our first term. And a common ratio of 2. So I'm going to just I'm going to circle that information. So I need it. And then part C, I'm going to write the argument for the sequence, the rule that'll allow me to find any number that I want in the sequence within reason. We can't find the really super large ones. That would be mean. So that'll be part C. So we'll start with A. And it says to write the first 6 terms in a geometric sequence. To do that, definition says we have to have the first term. And then to find the next terms, we multiply the first term times the constant. And then we multiply times the same number over and over again. So we start with 3. And to get to the next number, we have to multiply it times 2. To get to the next number, we have to repeat that times 2. Times 2, times 2, times 2. And there are the first 6 terms in our sequence using our A and our R. Part B asks you to write the 15th term. So this will utilize your formula A sub n. So if we want the 15th term, we're going to do the A sub 15th is equal to our first term times our constant ratio of 2 raised to the 15th power minus 1. And I'm interested to hear if anybody is curious why it's the n minus 1. Anybody? What do you think? Do you know? Well, this is the first term, so that takes care of that one. So we don't want to do 2 times 15 because we already have the first term. So we're going to raise 2 to the 14th power, and that'll get us out. So this is the first term, and then these are the next 14. Do you understand? Okay, so we get the 15th term is equal to 3 times 2 to the 14th power. And that is a big, big number. It's 16,384. Then we multiply times 3. So our 15th term is 49,152. And I believe that's exponential growth. Yes? That's a lot. That's a huge number to be only, 9 more terms out. Big. Okay, now part C, we're writing the formula so that we can find any term that we want. So we're just going to make it a general rule. So we're going to insert the n back into the problem. A sub n is equal to 3 times 2 to the n minus 1. Extension. What if I wanted you to write this as a summation? And I wanted you to find a geometric series instead of a geometric sequence. General summation of n starting with index 1, stopping at index k, whatever that is, for the rule 3 times 2 to the n minus 1. And just using your explicit rule. And then that's an extension. That's not a sequence. That's a series. Okay, it's just an extension because this is connected. Okay, all right. Next, find the 8th term of this geometric sequence that goes 9, 3, 1, dot, dot, dot. Now, of course, there's a lot of ways you could go about that. You could just work it out to 8 terms. But I say, let's do the a sub 8. What we have is our a. Yes, we have that. But what we do not have is the r. So what's the common ratio? What's happening over and over and over again? Multiplying by 1/3, you guys are seeing it. Now, if you're wondering, remember what I told how to find the ratio is you take the second term, divide it by the first term, and then you make sure that that pattern continues, and you do the third term divided by the second term. And are they equal?
Pardon the interruption. This is Mr. Bosch. Just a reminder, at 12:20, all freshmen, juniors, and seniors will be dismissed. You are expected to leave campus. Sophomores, you will have until 12:30 to report to your testing room.
Keep writing.
If you do not receive your testing room from your chemistry teacher or another teacher, they are posted, the room assignments are posted outside of the attendance office. So you'll have from 12:20 to 12:30 to go to your testing room. Thank you.
Okay, so we're going to take our A, we're going to take our R, I should have pressed pause. We're going to plug it into the formula, and we're going to find the 8th term, and we get the answer 1/243, which is really tiny. Exponential growth or decay? Decay, you got it. Okay, let's talk about a geometric means really quickly. Geometric means are very similar to arithmetic means, and you go about the same process to find it. They're just numbers that you insert between some numbers in a sequence. So you're going to set it between a first and a last number in a segment. And so the formula is pretty similar to the one we just looked at. The only thing that's different is we're going to consider the last term to be L instead of A sub n. So do we have to define this, or can I just do the L? Because everything else is the same. L is just the last term in the little segment versus the nth term. We're going to find some numbers that go between two numbers. So here we go. The same information as yesterday. So if you have to catch up, all you have to do is insert the word geometric for the word arithmetic. It's the same. Okay? So here we go, and we're going to be done. Insert two geometric means between.
Attention students, there will be no tutoring after school today.
Okay.
No tutoring after school today.
Okay, we got it. You okay? Go get a water. Go get a drink. Okay, so we're going to insert two geometric means between 4 and 256. So 4 was going to represent our A. 256 is going to represent our L. And here's what we need. And actually, how many terms are in our little sequence here? So we know that, and we know that. But what we need is, what are we multiplying 4 by to get to the next number? We need the R. We need it. So we just solve for R. 256 equals 4 times R to the 4 minus 1. Or 256 equals 4R cubed. Divide by 4. 64 equals R cubed. And at this point, you can go a couple of different directions. You can write this as 4 cubed equals R cubed and see R equals 4. Or you could cube root both sides, right? And you also get R equals 4. So here's what we know. We can multiply times 4 over and over again. 4 times 4 is 16. 16 times 4 is 64. So that's finding a geometric means. So your homework tonight is just to do 1 through 10, no summary.